Have you ever gazed up at the pale, luminous orb of the moon, suspended in the night sky, and felt a profound sense of familiarity? For as long as humanity has looked skyward, from ancient stargazers to modern astronomers, one particular aspect of our celestial neighbor has remained a constant source of quiet wonder and persistent curiosity. The moon always shows us the same face. Its craters, its vast, dark plains known as Maria, its subtle mountain ranges, all appear in precisely the same configuration, night after night, century after century. It is a cosmic truth that feels both ordinary, because we have grown accustomed to it, and utterly extraordinary, because it hints at a deeper, unseen dance playing out in the heavens. Imagine standing on Earth, watching the moon as it journeys across the sky, tracing its elegant arc from horizon to horizon. If you were to observe it over weeks or even months, you would notice that the familiar patterns, the shadows that create the illusion of a human face, a rabbit, or any other shape your culture has imagined within its features, never truly shift their position relative to your viewpoint. The same serene visage with its tapestry of light and shadow consistently looks back at us. This unchanging aspect is not merely an optical trick. It is a fundamental characteristic of the moon's relationship with our planet, a silent testament to powerful forces at play across immense cosmic distances. For millennia, this consistent appearance puzzled our ancestors. Without the benefit of advanced telescopes or the principles of celestial mechanics, it would have been easy to conclude that the moon simply did not rotate at all. Perhaps it was a celestial beacon, a lamp fixed in place, its illuminated side perpetually turned toward Earth. Such a simple explanation might satisfy the casual observer, but a moment of deeper reflection reveals a fascinating paradox. If the moon truly did not rotate on its axis as it circled our planet once every approximately 27 days, we would, over the course of its orbit, eventually see all of its surfaces. Picture an apple on a string being swung around your head. If the apple itself never spun, you would see its entire skin as it made its full revolution. Yet, this is precisely not what happens with the moon. Instead, the moon executes a more intricate maneuver. While it orbits Earth, it also rotates on its own axis, but at an exquisitely precise speed. This rotational period is almost perfectly synchronized with its orbital period. It takes the moon roughly the same amount of time to complete one full spin on its axis as it does to complete one full journey around Earth. This cosmic synchronicity is why the same lunar hemisphere is perpetually presented to our planet. It is a balance so finely tuned that it creates the illusion of stillness, a fixed gaze across the void, when in reality, a complex celestial ballet is continuously unfolding. Consider the intricate details we have come to know so well. The expansive, darker areas, the Maria, which were once mistakenly believed to be lunar seas, are prominently visible on this near side. These ancient basaltic plains, formed from volcanic eruptions in the moon's distant past, absorb more light than the lighter, more heavily cratered highlands. They create the familiar contrast that allows us to discern features like the man in the moon or the rabbit on the moon, cultural interpretations woven into the fabric of human folklore. These visual markers serve as unchanging anchors in the night sky, comforting in their predictability, yet holding within them the secrets of their origin. Every crater, every ray system extending outward from impact sites, every subtle elevation of the lunar terrain, all contribute to this single, immutable portrait. The constant presentation of the same face means that, for a vast expanse of human history, the very existence of another unseen side of the moon was a matter of pure speculation. Before the advent of space exploration, no human eye had ever directly witnessed this hidden hemisphere. It remained a realm of pure imagination, a blank canvas upon which science fiction writers and dreamers could project their wildest fantasies. Was it a mirror image of the side we knew, or was it utterly different? The very concept of a far side, distinct from a near side, highlights the profound impact of this synchronous rotation. It implies an area of the moon that is not inherently dark, as it receives just as much sunlight as the near side over the course of a lunar day, but rather one that is perpetually hidden from our terrestrial view, forever facing away. This celestial arrangement is not unique to our moon. Indeed, it is a common phenomenon in the cosmos, particularly among natural satellites that orbit larger planetary bodies. However, for us, observing it from our home planet, the moon's unchanging face has always been the most accessible and prominent example of this gravitational locking. It invites us to ponder the immense, invisible forces that govern the movements of celestial bodies, shaping their destinies over eons. The quiet, consistent presence of the moon, with its familiar patterns, serves as a natural clock, a calendar in the sky, and a constant reminder that even the most stable appearances in the universe are often the result of dynamic, intricate interactions. The fascination with the moon's constancy transcends mere scientific interest. It touches upon our deepest desires for stability and understanding in a vast, often bewildering cosmos. Its enduring presence, always presenting the same familiar contours, instills a sense of steadfastness, a rhythmic pulse in the nightly firmament. This profound observation, made by countless generations, has laid the groundwork for a deeper scientific inquiry into the mechanisms that forge such cosmic precision. It has prompted us to ask not just what we see, but why we see it, propelling us on a journey to unravel the gravitational whispers that dictate the celestial dance. The moon, with its unchanging face, whispers a story of ancient forces, of immense timescales, and of a delicate balance maintained across the silent expanse of space. To truly understand why the moon holds this eternal gaze upon our world, we must delve deeper, beyond the mere observation of its face, and explore the invisible yet profoundly powerful forces that govern its existence. The answer, woven into the very fabric of celestial mechanics, lies in the immense gravitational pull exerted by our own planet. Earth, far from being a passive observer, acts as a colossal, unseen sculptor, continuously shaping and guiding the moon through a cosmic dance of immense subtlety and incredible power. Gravity, as we commonly understand it, is the force that keeps our feet on the ground, that pulls apples from trees, and that holds planets in orbit around stars. Yet, this fundamental force is not uniform across vast distances. Its strength diminishes with the square of the distance between two objects. This might seem like a minor detail, a technicality of physics, but it is precisely this subtle variation in gravitational strength, this differential pull, that is the architect of the moon's constant presentation. This unequal tug across the moon's substantial diameter creates what we call tidal forces, a phenomenon far more profound than simply raising and lowering our terrestrial oceans. The moon itself, a world of rock and dust, experiences tides of its own, an almost imperceptible stretching and deforming under Earth's relentless influence. Imagine the Moon, a spherical body of significant mass, orbiting our planet. The side of the Moon that is closest to Earth experiences a stronger gravitational attraction than its center. Conversely, the side of the Moon that is furthest from Earth experiences a weaker gravitational pull than its center. This difference in gravitational force across the Moon's body attempts to stretch it, to pull it apart along the line connecting the centers of Earth and Moon. It is as if an invisible gargantuan hand is gently, but inexorably, trying to elongate our lunar companion. This stretching force creates two subtle yet immensely significant tidal bulges on the Moon. One bulge forms on the side directly facing Earth, where the gravitational pull is strongest, drawing the lunar material outward. The other, perhaps more counterintuitive, bulge forms on the side opposite Earth. Here, the explanation is slightly different. The main body of the Moon is pulled towards Earth more strongly than the material on its far side. This leaves the far side material, in effect, lagging behind, creating a bulge outward from the Moon's center, away from Earth. Thus, the Moon is not perfectly spherical. It is slightly elongated, like a very subtle egg, with its longest axis always pointing towards Earth. This deformation, though minor in terms of overall lunar dimensions, is absolutely critical to its synchronized rotation. These are not merely theoretical bulges, they are physical distortions in the Moon's rocky body. While the tides in Earth's oceans are dramatic and visibly responsive, the solid body tides on the Moon are, by comparison, minuscule. However, over geological timescales, millions and billions of years, even these subtle, constant deformations can have profound and lasting effects. When the Moon was younger, it was far more geologically active, with a molten interior and a more pliable crust. In this earlier, more plastic state, it was much more susceptible to the constant, kneading action of Earth's gravitational tides. The relentless gravitational pull of our planet effectively molded the Moon into this slightly ovoid shape, orienting its elongated axis along the Earth-Moon line. Consider the sheer scale involved. Earth is a colossal body compared to the Moon, possessing 81 times the Moon's mass. This immense mass translates into a gravitational field of overwhelming power. Even at the average distance of approximately 384,000 kilometers that separates our two worlds, Earth's gravity maintains an undeniable dominion over its satellite. It is a force that transcends the vacuum of space, reaching out with an invisible embrace, constantly influencing every atom of the Moon. This persistent gravitational interaction has been ongoing for billions of years, a continuous, unwavering tug and pull that has sculpted the Moon's very form and dictated its rotational fate. The formation of these tidal bulges is not an instantaneous event. It is a continuous, dynamic process. As the Moon orbits Earth, these bulges are constantly being formed and reformed. If the Moon were not already tidally locked, its rotation would carry these bulges out of alignment with the Earth-Moon axis. However, Earth's gravity would then exert a torque, a twisting force, on these misaligned bulges, attempting to pull them back into alignment. This constant effort to realign the bulges serves to slow down the Moon's rotation until it reaches a point where the bulges remain perfectly aligned with Earth. At this critical juncture, the Moon's rotation period matches its orbital period, and the tidal forces no longer create a braking effect. This is the state we observe today: synchronous rotation. The subtle, elongated shape of the Moon, molded by Earth's gravity, is like a permanent handle that Earth can grip. This handle ensures that the same side, with its distinct distribution of mass and its gravitationally induced bulge, is always the one facing Earth. It is a stable configuration, a gravitational equilibrium achieved over eons of cosmic interaction. Any tendency for the Moon to rotate faster or slower would be met with a corrective torque from Earth's gravity, gently nudging it back into its synchronous state. This process is a prime example of negative feedback in the cosmos, where a system adjusts itself to maintain a state of balance. Imagine the Moon in its early stages, perhaps rotating much faster than it does today. As it spun, the tidal bulges would constantly be dragged slightly ahead of or behind the direct line pointing towards Earth due to the Moon's rotation and its internal friction. Earth's gravity, always pulling most strongly on the nearest bulge, would then exert a persistent braking force on the Moon's rotation. This braking action, similar to applying a gentle, continuous drag, gradually transferred angular momentum from the Moon's rotation to its orbit, causing the Moon's spin to slow down and its orbit to subtly expand over billions of years. This cosmic dance of tidal interaction has not only locked the Moon's face, but has also been steadily, imperceptibly, pushing it further away from Earth, a process that continues even today, albeit at a rate of a few centimeters per year. The tidal forces have had another, more direct consequence for the Moon's physical characteristics. The near side, constantly stretched and pulled by Earth's gravity, has a thinner crust than the far side. This differential in crustal thickness is believed to have played a significant role in the Moon's volcanic history. A thinner crust would have made it easier for molten material from the Moon's interior to erupt onto the surface, forming the vast, dark maria that are so characteristic of the near side. The far side, with its thicker crust, resisted these eruptions more effectively, which is why it presents a much more heavily cratered, mountainous appearance with far fewer maria. Thus, Earth's gravity has not only locked the Moon's rotation, but has also fundamentally influenced its geological evolution, creating the distinct dichotomy between its two hemispheres. This understanding of tidal forces, the differential pull of gravity, and the resulting physical deformation of celestial bodies moves us beyond a simple description of the Moon's appearance. It provides a profound insight into the mechanics that govern the universe. It demonstrates that even the seemingly unyielding silence of space is filled with continuous, dynamic interactions. The Moon's unchanging face, which first sparked our ancient curiosity, is revealed not as a static image, but as the hard-won result of an ancient, ongoing conversation between two celestial bodies, a dialogue spoken in the language of gravitational force, sculpting one world in response to the other. This remarkable phenomenon, driven by the ceaseless pull of Earth, is a powerful reminder of the intricate and elegant laws that shape our solar system, ensuring that our Moon remains our steadfast, familiar companion, forever looking upon us with its singular, unchanging gaze. While Earth's tidal pull is the primary force behind the Moon's synchronous rotation, its effectiveness was greatly amplified by the Moon's own internal state during its formative years. To fully grasp this ancient ballet, we must travel back in time to a period when our Moon was a very different place, a world not of cold, stark rock, but of incandescent heat, partially molten and far more pliable than the satellite we gaze upon today. This early, geologically active phase was crucial, as it allowed the Moon's physical form to respond dynamically to the relentless gravitational kneading of its much larger neighbor. Scientists believe that soon after its violent birth, likely from a colossal impact between a Mars-sized protoplanet and early Earth, the Moon was an intensely hot body. The sheer energy of the impact, combined with the subsequent accretion of debris and the decay of short-lived radioactive isotopes, would have left the entire body, or at least a substantial outer layer, in a molten or semi-molten state. Picture a celestial object glowing faintly in the nascent solar system, its surface a swirling ocean of magma, its interior a cauldron of unimaginable temperatures and pressures. This was not a solid, rigid sphere, but a fluid, yielding entity akin to a cosmic blob. In this early, partially molten state, the Moon was exquisitely sensitive to external forces, particularly the powerful gravitational gradients emanating from the nearby Earth. A molten body, unlike a solid one, can deform much more readily. If Earth were attempting to create tidal bulges on a perfectly rigid sphere, the process would be far less efficient or perhaps even impossible. However, with a substantial portion of the Moon's mass in a fluid or highly plastic state, the gravitational forces could easily draw out and shape the lunar material, creating those crucial tidal bulges with greater ease and magnitude. The concept of a plastic moon is vital here. It means that the Moon's material could flow and adapt its shape under prolonged stress, rather than simply resisting it like a cold, unyielding stone. As Earth's gravity tugged at the Moon, drawing material towards itself on the near side and leaving material behind on the far side, the molten interior could respond, creating more pronounced and persistent bulges than would be possible in a completely solid body. These exaggerated bulges, in turn, provided Earth's gravity with a more effective lever to exert its rotational braking force. Think of it like trying to grab something with a smooth, perfectly round surface versus something with a slight handle. The more pronounced the bulges, the easier it was for Earth's gravity to grip the Moon and influence its spin. The internal friction generated by the continuous deformation of this molten material as the Moon rotated relative to Earth also played a significant role. This friction, acting like a cosmic brake pad, converted some of the Moon's rotational energy into heat, further contributing to the slowing of its spin. This energy dissipation within the Moon's interior was an essential part of the tidal braking mechanism, allowing the Moon to shed angular momentum from its rotation until it reached the stable, tidally locked state. This period of the Moon's geological activity also saw the formation of its distinctive surface features. The Maria, those dark, smooth plains predominantly found on the near side, are vast basaltic floodplains formed from ancient volcanic eruptions. The thinner crust on the near side, a direct consequence of Earth's tidal stretching, would have facilitated these eruptions. The relentless gravitational pull from Earth would have weakened and thinned the crust on the Earth-facing side, providing pathways for molten rock from the Moon's interior to rise to the surface. The far side, experiencing less direct tidal stress and possessing a thicker crust, would have been less prone to such extensive volcanic outflows, resulting in its more rugged, heavily cratered appearance, largely dominated by ancient highlands. The geological evidence strongly supports this history of a differentiated, partially molten Moon. Samples brought back by the Apollo missions, particularly the basaltic rocks from the Maria, reveal their volcanic origin and provide age dates consistent with this early period of intense activity. The relative scarcity of Maria on the far side also corroborates the theory of differential crustal thickness influenced by Earth's gravity. The Moon's internal structure, with its core, mantle, and crust, also tells a story of cooling and solidification over billions of years, transitioning from a hot, pliable body to the cooler, more rigid one we know today. Furthermore, the initial rotation rate of the Moon, immediately after its formation, is believed to have been significantly faster than its current tidally locked state. The conservation of angular momentum from the impact event that formed it would have imparted a rapid spin. This rapid initial rotation, combined with the Moon's partially molten state, created the perfect conditions for Earth's tidal forces to efficiently exert their braking effect. It was a race against time, as the Moon slowly cooled and solidified, becoming less plastic. But the tidal forces worked diligently enough, for long enough, to bring about the locking before the Moon became completely rigid and unresponsive. Without this phase of internal heat and fluidity, the outcome might have been very different. A completely solid Moon, even in close proximity to Earth, would have resisted deformation much more effectively. The tidal bulges would have been minuscule, and the tidal braking effect would have been significantly weaker, requiring an unimaginably longer period to achieve synchronous rotation, if it could ever be achieved at all within the age of the solar system. The Moon's molten past, therefore, represents a critical enabling condition, allowing the powerful gravitational influence of Earth to leave an indelible mark on its rotational dynamics. This journey into the Moon's ancient past underscores the profound interconnectedness of celestial bodies and the enduring power of fundamental physical laws. The Moon's present-day appearance and its stable synchronous rotation are not merely coincidental. They are a direct legacy of its fiery, tumultuous youth, when it was still malleable enough for Earth's gravity to sculpt its destiny. The subtle whispers of gravity, amplified by the Moon's internal heat, orchestrated a cosmic slowing down, bringing it to a state of perpetual alignment with our world. The image of a young, glowing Moon, slowly yielding to the gravitational embrace of the larger Earth, offers a powerful testament to the patient, persistent work of universal forces. It highlights how the internal properties of a celestial body, combined with the external forces acting upon it, conspire to determine its long-term evolution. The features we see on the Moon today, the distribution of its maria and highlands, its slightly non-spherical shape, are not merely static landscapes. They are echoes of a dynamic and transformative past. This period of geological activity and molten fluidity was not just a phase in the Moon's history. It was the very crucible in which its tidally locked fate was forged, forever ensuring that one side would always look upon Earth, a silent, unchanging sentinel in the night sky. The Moon's internal state, specifically its molten youth, was thus the fundamental ingredient that allowed Earth's tidal forces to work their magic, setting the stage for the synchronous rotation we observe with such familiarity today. It was the moment of malleability that allowed for the permanent embrace. Having explored the role of Earth's relentless tidal pull and the Moon's molten, pliable past, we arrive at the pivotal mechanism that unites these factors, the slow, inexorable process known as tidal braking. This cosmic dance of energy transfer is the key to understanding how the Moon, once likely spinning much faster, gradually slowed its rotation until it reached the precise, synchronized state we observe today. It is a testament to the patient, persistent work of gravity, enacted over billions of years, patiently reining in the moon's ancient momentum. At the heart of tidal braking lies the interaction between Earth's gravity and the tidal bulges it raises on the moon. As discussed, these bulges are formed by the differential gravitational force across the moon's body, creating an elongation along the line connecting the centers of Earth and Moon. If the Moon were already tidally locked, these bulges would remain perfectly aligned with Earth, and no further rotational influence would occur. However, in its early history, the Moon was almost certainly rotating faster than its orbital period around Earth. Imagine this scenario. The Moon is spinning on its axis while simultaneously orbiting Earth. If its rotation rate is faster than its orbital rate, the tidal bulges it develops due to Earth's gravity will not point directly at Earth. Instead, the Moon's rotation will drag these bulges slightly ahead of the direct Earth-Moon line. Picture the bulge on the near side being pulled forward, slightly leading the precise point directly facing Earth. Now, consider Earth's gravity acting upon these misaligned bulges. Earth exerts a gravitational pull on both bulges. The bulge that is slightly ahead of the direct Earth-Moon line will experience a gravitational tug that attempts to pull it back into alignment. This tug, exerted on the leading bulge, creates a torque, a twisting force that opposes the Moon's rotation. It acts like a cosmic brake, slowly but surely sapping angular momentum from the Moon's spin. Simultaneously, the bulge on the far side of the Moon, which is also slightly misaligned, would experience a corresponding tug. However, due to the inverse square law of gravity, the gravitational force exerted by Earth on the nearer, leading bulge is stronger, and thus has a more dominant braking effect. The net result is a persistent, gentle yet incredibly powerful rotational braking force that acts to slow the Moon's spin. This is the essence of tidal braking. The energy for this braking action does not simply disappear. According to the fundamental laws of physics, angular momentum must be conserved within the Earth-Moon system. As the Moon's rotation slows, the angular momentum it loses from its spin is not annihilated. Instead, it is transferred to the Moon's orbit around Earth. This transfer of angular momentum has two primary consequences for the Moon's orbital characteristics. It causes the Moon to slowly recede from Earth, and it also subtly increases the length of Earth's day. The Moon is, in fact, still very gradually moving away from Earth at a rate of approximately 3.8 centimeters, about 1.5 inches, per year. This tiny, almost imperceptible outward spiral is a direct, ongoing legacy of tidal braking, even though the Moon is now tidally locked. The slight remaining tidal forces continue to cause a tiny exchange of angular momentum, pushing the Moon further into its orbit. Concurrently, as angular momentum is transferred from the Moon's rotation to its orbit, there is also a reciprocal effect on Earth. Our planet's own rotation is gradually slowing down, leading to a minuscule lengthening of our days. Billions of years ago, Earth's day would have been considerably shorter, perhaps just a few hours long. This fascinating interplay highlights the deep interconnectedness of celestial mechanics, where changes in one body inevitably influence the other. The efficiency of this tidal braking process was significantly enhanced by the Moon's partially molten interior, as discussed earlier. The internal friction generated by the deformation of the Moon's fluid material as it rotated ahead of its bulges would have been much greater than in a solid body. This friction converted rotational energy into heat, dissipating it from the Moon's spin and making the braking process much more effective. Without this internal energy dissipation, the Moon would have resisted the tidal forces more strongly, making the journey to synchronous rotation far longer, or perhaps even incomplete. Over the vast expanse of cosmic time, billions of years, this constant, subtle braking force brought the Moon's rotation rate into perfect alignment with its orbital period. Eventually, a stable equilibrium was reached. At this point, the Moon's spin rate matched its orbital rate. This meant that the tidal bulges, no longer being dragged ahead, settled directly along the Earth-Moon axis. Once the bulges were perfectly aligned, the braking torque ceased, as there was no longer any misalignment for Earth's gravity to correct. The Moon had achieved synchronous rotation, forever presenting the same face to Earth. This entire process is a prime example of a celestial body evolving towards a state of minimum energy. The tidally locked state is the most stable gravitational configuration for a satellite in close orbit around a more massive primary body. It minimizes the energy expenditure required to maintain its orbit and rotation, representing a kind of cosmic comfort zone where the gravitational forces are in a harmonious balance. Once achieved, this state is incredibly stable and resistant to disruption, ensuring that the Moon's face remains fixed in our sky for eons to come. It is important to remember that this was not a sudden event, but a gradual, relentless process. The Moon didn't simply snap into synchronous rotation overnight. Instead, it was a slow, majestic pirouette that took billions of years to complete. From its rapid initial spin, fueled by the violence of its formation, to its current stately rotation, the Moon has been patiently guided by the invisible hand of Earth's gravity, transferring energy and angular momentum until equilibrium was found. The observation of synchronous rotation is not unique to the Earth-Moon system. Many other natural satellites in our solar system exhibit this phenomenon. For example, the large moons of Jupiter, Io, Europa, Ganymede, and Callisto are all tidally locked with their colossal parent planet. The same is true for most of Saturn's moons, including the enigmatic Titan. This widespread occurrence across different planetary systems underscores the universality and power of tidal forces and tidal braking as fundamental mechanisms in shaping the dynamics of planetary systems. It demonstrates that our Moon's unchanging face is not an anomaly, but a common outcome of gravitational interaction between a primary body and its satellite. The precision of this locking is also quite remarkable. While the Moon's rotation and orbit are nearly perfectly synchronized, there are minor variations. These include slight librations or wobbles in the Moon's orientation as seen from Earth. These librations are caused by the fact that the Moon's orbit is not a perfect circle but a slight ellipse, and it is also tilted relative to Earth's equator. These minor wobbles allow us to peek just slightly around the edges of the Moon's near side, revealing approximately 59% of its surface over time, rather than precisely 50%. However, these librations are small and do not fundamentally alter the fact that one hemisphere is always predominantly turned towards us. The effect of tidal braking is so powerful that it overwhelms these minor orbital eccentricities, maintaining the locked state with unwavering consistency. Therefore, the slow dance of tidal braking is more than just a scientific explanation. It is a narrative of cosmic evolution. It tells a story of how gravity, acting over immense timescales, can reshape not just the orbits of celestial bodies, but their very rotational destinies. The Moon's unchanging face is a frozen moment in time, the culmination of a billion-year process where Earth's gravitational embrace gently yet firmly guided its satellite into a perpetual, synchronized waltz. It is a subtle testament to the elegance and power of the universe's most fundamental laws, continually shaping and refining the celestial mechanics that define our place within the cosmos. The Moon's current state is a stable, hard-won victory of persistent gravitational influence, allowing us to forever gaze upon its familiar face, a silent reminder of the profound forces at play beyond our terrestrial sphere. The culmination of Earth's relentless gravitational pull, the Moon's molten past, and the slow, persistent process of tidal breaking is a celestial phenomenon known as synchronous rotation. This is the precise cosmic ballet where the Moon's rotational period, the time it takes to complete one full spin on its axis, perfectly matches its orbital period, the time it takes to complete one full journey around Earth. It is this exquisite synchronicity that is the ultimate reason why we are forever presented with the same lunar face, a stable and enduring consequence of billions of years of gravitational interaction. To fully appreciate the precision of synchronous rotation, consider the delicate balance it represents. The Moon orbits Earth approximately once every 27.3 Earth days. Simultaneously, it rotates on its own axis exactly once every 27.3 Earth days. If it spun even slightly faster or slower, the effect would be immediately apparent over the course of its orbit, and we would begin to see different portions of its surface. This perfect one-to-one correspondence between its rotation and revolution is not a coincidence. It is a state of gravitational equilibrium, meticulously achieved and maintained by the pervasive forces of tidal friction and torque. Imagine a celestial dancer performing a slow, graceful pirouette while simultaneously circling a much larger partner. The dancer's body is always oriented towards its partner, even as it moves through space. This is the Moon's choreography. As it travels along its elliptical path around Earth, its internal clock, its axial spin, ticks at precisely the same rate as its external clock, its orbital journey. The synchronization is so exact that any deviation, any minute acceleration or deceleration in its rotation would immediately be corrected by Earth's persistent gravitational grip on the Moon's tidal bulges, gently nudging it back into perfect step. This tidally locked state is incredibly stable. Once achieved, it requires significant external forces to disrupt it. For a body like the Moon, which has long since solidified and cooled, becoming more rigid, the process of further tidal breaking largely ceases. The bulges are already aligned, and the breaking torque has dissipated. The system has found its lowest energy state, a point of gravitational contentment where no further major exchanges of angular momentum are necessary to achieve alignment. This stability is why, for the entirety of human civilization, the Moon's face has been a fixed point of reference in our night sky, its familiar features a testament to this cosmic locking. The consequence of synchronous rotation is profound for us on Earth. It means that while the Moon technically spins, it never turns its back on us. The hemisphere that faces Earth, often referred to as the near side, is always the one illuminated by the sun for a certain period during its lunar day, and then plunged into darkness just like any other spinning celestial body. However, from our perspective, we consistently view this particular hemisphere. This is why the term dark side of the Moon is a common misconception. The far side receives just as much sunlight over a lunar month as the near side. It is simply the hidden side or the far side, perpetually averted from Earth. This constant presentation has shaped human mythology, observation, and scientific inquiry for millennia. All the features we have come to know, the prominent Maria like Mare Tranquillitatis, where Apollo 11 landed, or the distinctive ray craters like Tycho, with its bright streaks extending across the surface, are all visible because they reside on this near side, a landscape forever etched into our collective consciousness. Without synchronous rotation, our view of the moon would be constantly shifting, presenting new and unfamiliar vistas with each lunar cycle, altering our fundamental relationship with our closest celestial neighbor. The forces that brought about synchronous rotation are a beautiful demonstration of the universality of physical laws. The principles of gravity, angular momentum, and energy dissipation are not unique to the Earth-Moon system, but are fundamental to the dynamics of celestial bodies throughout the cosmos. This phenomenon is a natural outcome for satellites that orbit sufficiently close to a more massive primary body, especially if they possess enough internal fluidity in their early history to allow for efficient tidal braking. This widespread occurrence, from the moons of Jupiter and Saturn to exoplanets orbiting close to their parent stars, underscores that synchronous rotation is not an isolated quirk of our moon, but a common, predictable state of orbital evolution. Consider the timescale involved. The moon formed approximately 4.5 billion years ago. The process of tidal braking and the eventual achievement of synchronous rotation would have taken hundreds of millions, possibly even a billion years. This vast temporal canvas highlights the patience of cosmic forces. What appears to us as a static, unchanging relationship is, in fact, the end product of an immensely long and dynamic evolutionary journey. Our current view of the moon is therefore a snapshot, a moment of gravitational harmony that has been diligently sculpted over eons. The stability of synchronous rotation is also influenced by the moon's internal mass distribution. Due to the tidal forces, the moon is not perfectly homogeneous. There are subtle variations in the density and thickness of its crust and mantle. These mass asymmetries, often called mascons, create slightly stronger gravitational attractions towards certain points on the moon's near side. These are regions of concentrated mass beneath the lunar surface, often associated with the large Maria. These mascons act like additional gravitational anchors, further stabilizing the moon in its tidally locked orientation. Earth's gravity naturally prefers to pull on these denser regions, ensuring that they remain oriented towards our planet, effectively preventing the moon from rotating away from its synchronized state. This intricate dance of gravity and geology, culminating in synchronous rotation, has made the moon a unique object of study. Its distinct near and far sides offer a natural laboratory for understanding planetary evolution. The near side, with its thinner crust and abundant Maria, tells a story of intense volcanic activity, likely influenced by the constant stretching and heating from Earth's tides. The far side, with its thicker crust and heavily cratered highlands, provides a contrasting narrative, suggesting different geological processes and a different response to ancient bombardments. The very act of synchronous rotation, by preserving these two distinct geological records, provides invaluable insights into the early solar system. Moreover, the synchronous rotation of the moon has implications for future space exploration and lunar habitation. Any permanent base on the near side would have a constant, uninterrupted line of sight to Earth, facilitating communication and observation. Conversely, A base on the far side would be shielded from Earth's radio interference, making it an ideal location for radio astronomy, as it offers a quiet, electromagnetically pristine environment for observing the universe. The fixed orientation of the Moon, therefore, isn't just a curiosity. It's a fundamental parameter that shapes our strategies for interacting with our celestial neighbor. In essence, synchronous rotation is the elegant resolution to the gravitational tug-of-war between Earth and Moon. It is the state where the Moon's shape, its mass distribution, and its spin rate have found a perfect balance in response to Earth's overpowering gravity. This stable configuration ensures that the particular hemisphere of the Moon that faces us today has been gazing upon Earth for billions of years, a silent, unwavering companion in our cosmic journey. This perpetual face, with its familiar patterns, is not merely a static image. It is a living, enduring monument to the profound and intricate laws that govern the universe, a testament to the patient and powerful work of gravity that has shaped the very character of our closest celestial world. The Moon's locked face is a profound reminder that even in the vastness of space, there is an intimate and enduring connection between celestial partners. For millennia, the Moon's far side remained a tantalizing mystery, a blank slate that fired human imagination. Known only as the hidden side or the dark side, a misnomer as it receives just as much sunlight as the near side over the course of a lunar month, it was a realm entirely unseen by human eyes. Our ancestors could only wonder what lay beyond the terminator, the line separating light from shadow, on the hemisphere perpetually averted from our gaze. This profound veil of secrecy finally began to lift in the 20th century, ushering in an era where humanity could, for the first time, truly see the entirety of its celestial companion, revealing a landscape strikingly different from the familiar face we had always known. The momentous unveiling occurred on October 7th, 1959, when the Soviet Union's Luna 3 spacecraft executed a flyby of the Moon. This pioneering probe transmitted the first-ever blurry, low-resolution images of the lunar far side back to Earth. It was a triumph of engineering and a groundbreaking moment in space exploration, offering humanity its initial glimpse into the previously unknown. What these early images revealed was not a mirror image of the near side, but a distinctly different terrain. Far fewer Maria, those vast, dark basaltic plains, and instead a much more heavily cratered, rugged surface dominated by ancient highlands. It was a landscape that immediately sparked new questions about the Moon's geological history and formation. Subsequent missions, notably NASA's Lunar Orbiter program in the mid-1960s, provided increasingly detailed and comprehensive photographic maps of the far side. These missions were crucial for selecting landing sites for the Apollo missions, as they revealed the full complexity of the lunar surface. The high-resolution images confirmed the earlier findings. The far side was indeed a more heavily scarred, mountainous region, a testament to billions of years of cosmic bombardment, with only a scattering of smaller Maria compared to the expansive dark patches that characterize the near side. The stark contrast between the two hemispheres became a central puzzle for lunar scientists. Why was the near side dominated by vast, smooth plains, while the far side presented a more ancient, pockmarked appearance? The answer, as we have explored, is deeply intertwined with Earth's tidal forces and the Moon's early, molten history. The gravitational stretching from Earth thinned the crust on the near side, making it more susceptible to volcanic eruptions that filled large impact basins with molten basalt, forming the Maria. The far side, with its thicker crust, resisted these eruptions more effectively, preserving its ancient, cratered landscape. Thus, the very force that tidally locked the Moon also helped sculpt its distinct hemispheric dichotomy. One of the most remarkable features discovered on the far side is the South Pole Aitken Basin, an immense impact crater that is one of the largest and oldest known impact structures in the entire solar system. Measuring approximately 2,500 kilometers, 750 miles, in diameter, and up to 13 kilometers, 8 miles deep, it is a colossal scar that dominates the southern portion of the far side. This basin is a window into the Moon's deep past, potentially exposing material from the lunar mantle, offering invaluable clues about the Moon's internal composition and early evolution. Its sheer scale underscores the violence of the early solar system and the Moon's enduring record of that tumultuous era. The exploration of the far side continued with robotic landers. In a historic first, China's Chang'e 4 mission successfully landed the Yutu-2 rover in the South Pole Aitken Basin in January 2019. This unprecedented achievement marked the first time any spacecraft had ever made a soft landing on the Moon's far side. The mission has been instrumental in gathering scientific data from this unique region, studying its geology, composition, and the radiation environment, providing direct insights into a part of the Moon that was once utterly inaccessible. The data returned by Yutu-2 continues to deepen our understanding of lunar processes and the evolution of rocky bodies. The far side also holds significant potential for future scientific endeavors, particularly in the field of astronomy. Because it is permanently shielded from the radio noise and electromagnetic interference generated by Earth, the far side is considered an ideal location for radio telescopes. Imagine placing powerful radio observatories in this radio-quiet zone, free from the constant cacophony of human transmissions. Such telescopes could detect faint signals from the early universe, allowing scientists to peer back in time to the cosmic dark ages before the first stars and galaxies fully ignited. This unique environment makes the lunar far side a prized location for pushing the boundaries of astrophysical research. Beyond scientific research, the Moon's far side also represents a frontier for future human exploration and potential colonization. Establishing permanent outposts there would require overcoming significant engineering challenges, including autonomous power generation, communication relays to Earth, as direct line of sight is blocked, and robust life support systems. However, the benefits such as access to unique scientific resources, pristine observational conditions, and the strategic advantage of a secluded location make it an attractive prospect for long-term lunar presence. The lessons learned from robotic missions like Chang'e 4 are paving the way for these ambitious future undertakings. The journey from speculation to direct observation of the Moon's far side is a powerful narrative of human curiosity and technological advancement. It underscores that even the most enduring mysteries of our universe can be unraveled with persistent inquiry and ingenious exploration. The images and data from the far side have not only satisfied our ancient longing to see what was hidden, but have also fundamentally reshaped our understanding of the Moon as a dynamic, complex world with a rich and varied history. The Moon, in its entirety, is now a known entity, no longer a half-seen enigma. In contemplating the hidden side, we are reminded that our universe is full of such unseen marvels awaiting discovery. The Moon's familiar face, Eternally gazing at Earth is a constant invitation to look deeper, to question what seems self-evident, and to understand the profound forces that shape the cosmos around us. Its far side, once a realm of pure imagination, is now a testament to what humanity can achieve when it dares to venture beyond the known. The story of the moon's locked face and its hidden side is a grand testament to the enduring power of gravitational forces, a silent conversation between celestial bodies that began billions of years ago and continues to shape our perception of the cosmos. It reminds us that even the most seemingly simple observations, like the unchanging face of the moon, often conceal layers of profound scientific truth and cosmic elegance. Our journey through the moon's ancient history, its molten youth, the relentless work of tidal breaking, and the eventual exquisite balance of synchronous rotation culminating in the revelation of its far side, has illuminated this wonder. And so, as you next gaze upon the moon, perhaps a new appreciation will settle upon you. Its familiar craters and Maria are not merely static decorations in the night sky. They are the visible record of a long, intricate dance, a gravitational ballet performed over unimaginable timescales, resulting in the serene, unchanging presence that has comforted and inspired humanity for all of its existence. It is a cosmic constant, a testament to the elegant laws that govern our universe. Thank you for exploring this quiet mystery with me. If you found solace and curiosity in this journey through the moon's hidden electrical web, please do tap the like button and subscribe to the channel. And if you'd like to know when the next quiet exploration drifts into view, you can click the notification bell. That way, you won't miss the next soft science for a gentle mind.